In this section, we're going to learn about the photoelectric effect. Albert Einstein won his Nobel Prize for explaining the nature of this effect. The photoelectric effect was a well-known phenomenon by 1905 when Einstein explained it. Basically, if you shine a light on a metal surface, if the light has the proper frequency, the metal surface will give off electrons. Now, ideally, at this point, we would have you run a photoelectric effect simulator. There are those available online. And if you were to run it, you would find out what different properties the photoelectric effect has. The questions you would answer would be questions like these. What effect does changing the wavelength of light have on the emitted electrons? We would look at how much the energy of the emitted electrons have. And when we look at these electrons, we're going to look at the energy, the most energetic of the electrons. And we would look to see if there's a cutoff frequency. That is to say, is there a frequency that below which no electrons are going to be emitted? And then we would look at what effect does changing the intensity of a light have. These were things that had been studied about the photoelectric effect before Einstein wrote his paper. If you have a chance to run the simulation, it's worthwhile doing. But to save some time, let's just cut to the end here. It turns out that in the photoelectric effect, the electrons that get released have a very well-defined maximum kinetic energy. It's not random. There is a certain maximum kinetic energy the electrons can have for a given frequency of light. And the kinetic energy, maximum kinetic energy, is proportional to the frequency of the light that you use. So the higher the frequency, the higher the maximum kinetic energy of the electrons that are emitted. Surprisingly, the maximum kinetic energy doesn't depend on the intensity of light. Here we see something that probably doesn't agree with a wave picture of light. You would expect that if you have a more intense light beam, that means the waves have a larger amplitude, then the kinetic energy of the most energetic electrons would be larger. And it also turns out that there is a frequency below which no electrons get emitted, no matter how intense the light is. So here's what we would expect with a wave model of light in the photoelectric effect. Let's say we have a light wave of a greater intensity. It should cause the electrons that are given off to have more energy, at least the most energetic electrons. So here's a wave with a relatively small intensity, and it gives off a very slow-moving electron, i.e. not a lot of energy. But we have a incoming light wave that has a greater intensity, i.e. more energy, and it gives off an electron that has a faster speed, more kinetic energy. We would also expect that a light wave of any frequency should eventually transfer enough energy to release an electron. However, as we have already discussed, the photoelectric effect didn't seem to fit what the wave model of light was showing us. So in 1905, during Einstein's miracle year, he took Planck's suggestion that light emitted from blackbody radiators is emitted in particles, which he called quanta. Einstein took that idea and decided to say, well, what if light is always a little particle instead of a wave? Would that explain the photoelectric effect? And the answer is it would. Let's see what happened here. We know that we don't get more energetic particles when more intense light hits it. Now, in a particle view, the more intense light would just mean you have more particles, because the frequency of the light determines the energy of each particle, as Planck suggested. So, in Einstein's model, if you had one photon coming in, one electron would be emitted. Another photon comes in, another electron gets emitted. So the more energetic light, the more intense light, just means more electrons get emitted, and that's exactly what we see happening. Einstein's particle model explained all of the features of the photoelectric effect better than the wave model did. A more intense light beam, meaning it has more photons, is going to produce more electrons, but it is not going to increase their maximum kinetic energy. The kinetic energy of the electrons should increase if you increase the energy of the incoming photons, which means you make them have a higher frequency. And because there's a certain amount of energy required to pull an electron off of a piece of metal, photons below a certain frequency will not have enough energy to release the electron regardless of the intensity of the light. So there will be a cutoff frequency. This is Einstein's equation for the photoelectric effect. It says that the maximum kinetic energy of electrons emitted in the photoelectric effect is equal to the energy of the incoming photons, which Planck said was h times f, minus the work function. The work function is the minimum amount of energy required to pull an electron off of the metal. Let's do a very simple example so you can see how this works in practice. Let's say we have a beam of light that has photons with 5 electron volts of energy. When this light strikes a metal plate, electrons with a maximum of 3 electron volts of kinetic energy are released. What is the work function of the metal? I don't think I need to pause the video. You can work this question out in your heads quite quickly. The answer is 2 electron volts. Conservation of energy would say that if 5 electron volts are going in, and the kinetic energy of the released electrons is 3 electron volts coming out, then the work function must be 2 electron volts. Let's take a look at how one actually does a photoelectric experiment. The first successful one to verify Einstein's equation was done by Robert Millikan, who was the same person that discovered the quantization of charge on the electron. And it took to 1916 before this experiment could be done. It was quite a subtle experiment. Involved working with metals that had to be very pure, and they had to be done in a vacuum. So Millikan had to come up with a way of actually shaving off a piece of the metal so that you'd get a fresh exposure of the piece of metal in order to do the experiment with it. And this had to be done inside of a vacuum tube. What Millikan did inside of this vacuum tube was to apply a potential to the metal plate that was being hit with the light that was releasing the electrons, and the potential would go against the motion of the electrons. So the electrons would give up some of their kinetic energy they gained from the photons, and he would then determine how much potential was necessary to give the electrons to stop moving at all. The formula then, if the kinetic energy of the electrons, the maximum kinetic energy of the electrons, it would be their charge times the stopping potential, because that would mean that that was the energy, the potential energy the electrons gained, and they gave up the kinetic energy. And so in Millikan's formula, the electron charge times the stopping potential, the minimum potential necessary to stop the electrons, is going to be equal to the energy of a single photon minus the work function. Here's a picture of Millikan's graphs from his 1916 paper. This was long before we had computers that could do all of the calculations for us. And so they had to, by hand, graph these data and then use the intercept of the graphs to figure out what the stopping potential was for a given frequency of light and a given kind of metal. You can see the wavelengths of light written on the lines that are graphed here. Now Millikan called his experiment a direct photoelectric determination of Planck's H, because that's what this experiment allows us to do. It allows us to determine what Planck's constant is. Here was our formula from before. We took Einstein's formula and just changed the kinetic energy maximum to the charge on the electron times the stopping potential, the minimum potential necessary to cause the electrons not to make it all the way across the potential difference. And you just divide both sides of that equation by E, and you get that the stopping potential is equal to h over E times the frequency minus the work function divided by the electron charge. So you can see from this graph that if we were to graph the stopping potential versus the frequency, the slope of that line should be Planck's constant divided by the electron charge. And of course, by this time, Millikan had already figured out what the electron charge was. And so this gave us a way to determine experimentally what Planck's constant was. Here are the data that one can derive from Millikan's original experiment. For different frequencies of light have different stopping potentials. If you were to graph the stopping potential versus the frequency, your slope should be equal to h over E. When you do this graph, you will note that there is a horizontal intercept. The kinetic energy is equal to the energy of a photon minus the work function. So if the photons do not have sufficient energy in order to release one electron, then no electrons get emitted. So the maximum kinetic energy is equal to 0 for some frequency of light that we call the cutoff frequency.